Oh no, it's 5 colorable. Sorry. It's also 6. You can prove it by discharging. In 5 colorable. This is the keyword. Okay. We prove this by discharging. Okay. We start with G's counterexample, as we said. Minimal counterexample. G's, we can assume G is 6 critical. So G is not 5 colorable, but every proper subgraph is 5 colorable. Yes. If our theorem is not true, then we will have such graph. So by assuming that G is 6 critical, we know we don't have vertices. We don't have in other words, minimal degree of G is at least 5. We must have 5 vertices by Euler formula, yes? Okay? We take one reducible configuration, just one. A reducible configuration. Two triangles, and here's our vertex. Here's arbitrary. First, in my planar graph, in my G, is it clear that I don't have here the edge? I don't have this edge here in the plane? Why it is clear? Because if I have this edge, look also this is a triangle now, yes? This thing is triangle, yes? And I have something inside and something outside. This means like if I draw it a little bit again here, this red tricycle is like this, and then I have something here, and then I have something here. It is a click cut. Click cut. It means set of vertices which form click, and when I remove graph, 2 or more parts. And what we proved yesterday, critical graph don't have click graph. So I don't have such a. So this means these vertices x and y are not adjacent. So x and y are not adjacent. Otherwise, we get click graph. click cut. Click cut. Okay? So they are not adjacent. I can remove this part as here. Okay. So can you see? Does anybody see? Does anybody see how I reduce this now? That my G doesn't contain such a configuration. What I will do next. Okay, I will explain it. I will identify X and Y. I will remove this edge, remove this, and identify. I will do like this. Let's say this is vertex A with other colors. Let's use B, C. I will do like this. And here's some maybe. So I will get like this. I identify X and Y. Here is A, here is B, here is C. And I'm going to have some edges here and there, yes. Maybe I'm going to have some edges here, no, this is the 5 vertex, this is the 5, sorry, I was too, I have to move this down a little bit. My 5 vertex, I will denote it with D, yes. Okay? Sorry?
Subdividing AD or what?
I remove A and D. I remove it. I remove A and D and then identify X and Y. Okay. We get smaller graph. Our graph was smaller counterexample, yes, and critical, yes, and we get smaller graph. So this graph should be 5 colorable, yes. Okay, are we okay with it? It's 5. So this can be colored. Okay. So this has coloring. Let's say just by random, 1, 2, 3, 4, 5. Maybe some of these colors are the same. And when we go back, okay, so what I deduce when I go back, I know this is 3, this is 4, this is 1, and this is 1. X and Y have color 1, but it's okay, they are not adjacent, yes? We showed it before. We showed it before, otherwise we have clicked. And here is maybe some color 5, yes? So we have 5 vertices around D, but 2 of them are same colored. Yes? X and Y are same colored. Sorry? Should be? Yeah, okay, yeah, okay, yeah. Yes. Some permutation of the colors. Yeah. 2. Okay, I'm a little bit. And now we have to D, yes, okay. it may have this, it may happen here is 1, yes? It may happen. But I uncolor here D. I uncolor. And now I count. I have 5 vertices. 2 vertices are colored the same. 1 is free color. I don't care what is 1. 1 will be free. Because it may happen here is 1, 1, then I have to recolor. If it is not this the same, then I leave it. But whatever, I just, when I go back, I will again color the paint I will have is the same, yes. This is how I prove, this is how I prove this configuration is reducible. Okay, do you follow it?
Edge 80 there, still I can color the
Which edge?
80. If I just identify X and Y.
It's not there. How you will keep it? You identify this like this. You remove this, and inside the face, you identify. In order to preserve that your new graph will be still planar. Sorry, I didn't explain too. I thought maybe you know it. But you cannot just keep A and D. Because if you want to keep it here A and D, yes, and here are edges, graph maybe will not be planar anymore. Okay? So you lose it here just to save planarity because you want to stay in the planar graphs. And then you back, maybe A and D are the same color, maybe a differently colored. You don't care. You just recolor D with the free color. You have 4 forbidden colors. The 5th one is free. Okay? This is it. So we prove that we don't have 2 triangles with 5 vertices, one of these 2 vertices. This is our, so again, this is important. This will save us charge. This will help us to be positive everywhere. So we do not have five. Okay. Now, our rules. We're going to have one rule. Just to be simple, I choose something like that. So our rule will be like this. Rule R1. We have a 4 or more face, so we have face of size 4 or more. I will illustrate it. And we have here 5 vertices. Okay. This face will send to this 5 vertex 1/2. With words, the rule says every 4 or plus face donates 1/2 to each incident 5 vertex. Okay? Maybe this is nicer. This is our rule. Okay? So, let's see the final charge. What happened with the final charge? So initial charge was this. So V is degree of V minus 6. and C at F was 2 length of the face minus 6, initial charge, okay. What changed? In this graph, do we have 3 vertices? 2 vertices, 1 vertices, 4 vertices? We don't have. Our graph is critical and the minimum degree is 5. So, if final charge if first the easy things, let's get rid of the easy thing. If vertex is of degree at least 6, what happens? Final charge I will denote by C. In that case, final charge of V, 6 vertex, 7 vertex, they don't change. The final charge will be the same like initial charge, and it will be like dV minus 6, and it will be bigger or equal to 0. Okay? 7, 6, 7, 8, 9, 10, and so on vertices have positive charge. 1, 2, 3, 4 vertices we don't have. We don't have. Okay. Now, let's see the 5 vertex. How many triangles we can have here? Two. One here and one here. They are not adjacent, yeah? Okay. If we have another triangle, says here, then we're gonna have the reducible configuration, yes? That's not allowed it. Or here, then we have this reducible configuration. Or if here, we can have plenty of them. So, here, by knowing that two adjacent triangles, by knowing that this is a reducible configuration, I will copy down. This is reducible. By knowing that this is reducible, we know that we have here how many big faces of size at least 4? 3. Even 2 are enough. So look, this will send 1/2. This is the rule, yes? 1/2 face of size 4 or more, send 1/2 to a 5. 1/2, 1/2, 1/2. The final charge of the final charge of a vertex of the 5 vertex V, 5 vertex V. The final charge will be initial charge, at least it may gain not 3 times in 1/2, it may get 4 times or 5 times if you don't have triangle. At least 3 times 1/2, it is like my initial charge is -1, and then 3 1/2, it will be bigger or equal to 1/2. So we will see 5 vertices when I get positive, strictly positive. What happened with faces? Triangle has initial charge 0. Triangle do nothing. It stay, yes. If we have of a triangle will be the same as the beginning, it will be 0. Okay, let's see the for filling. We can do it at once, but let's see for four face. Initial charge is 2 4 multiply 4 this -6, like 8 minus 6 is 2, yes? Initial charge is 2, and it can send how many? 1/2 to every vertex, yes? 1/2 multiplied 4, and it will be at least this, yes? It may not send anything, so it will be, and this is 0. Let's see 5 phase. Initial charge is 2 multiplied 5 minus 6 is 4. It sends at most 5 halves, and this is like 3, 5. And so on. Actually, we can do that at once. Initial charge of phase is like, final charge of phase is initial charge, at least, yes, we can, at least, initial charge of phase minus the length of the phase, because every vertex we see can get length of the phase over 4. And if you do like this is 2 length of f minus 6, yes, this is initial charge, minus length of f over 4. That will be like, when is that somewhat? Half. Yes. Okay. So we're going to have 3 over 2, yes, a length of f minus 6, yes, and this is bigger or equal to 0, because f is at least 4. For f, a length at least 4, as L increases, it's even bigger. So, and this is the end of the proof, yeah? Yeah?
Basically, in that reducible configuration,
Yeah.
what was the role of 5 vertex?
What was?
What was the role of 5 vertex? Rule of 5 vertex. I mean, it was still reducible if you don't take the vertex to be a 5 vertex.
I don't think so. Because, a good question is no way, because I have here, let's say, 100 gas, and then I identify A and B as C, D, this is like X1, X2, and so on. I remove this, I identify this, and then I go back, then I C, A, D, B, and here I have many different colors. This will be the same color, another one.
A and B like we did previously.
So,
We can still merge A and B like we did previously.
yes, this is the same color. Color 1. And here's color 2, and here's color 3, 4, 5. So what are you going to do? What?
We can repeat color 2 that has been appeared on vertex C.
What we have the color C here, yes? You would have here many different colors. So it is not that easy. Doesn't work. Okay? So this is one such simple example with one reducible configuration and with one reducible rule, yes. Okay? I will go back to the slides and I will talk about the 4 color again, because we have like what, 15 more minutes, 20 more minutes, yeah, we just, with the slides, yes. So we prove this, what is here. Independently, because we, discharging method get developed, appear one theory which is called light theory, which study some spatial configuration in the plane under some condition, yes, small such topic. And here are two results. Coating proved examples of such results in this light graph theory. Coating theorem is that if G is a three-connected planar graph, then it must exist some edge with the sum of its n degrees, in total at most 13. So we have three-connected graph, then you will find vertex, edge, you will find edge in three-connected planar graph, yes, such degree of A plus degree of B at most 13. And this is tight bound. If you take icosahedron, do you know what is icosahedron? It's like 12 vertices, all of degree 5, yes. Icosahedron looks like this. Icosahedron looks like we have, I will not draw it the whole locally. I can draw it all, but it's not necessary. It is only one here, yes. Yes. And locally at every face looks like this. Triangle is every face, and all faces are of degree, I drew it too much edges, and all vertices of degree 5. It looks locally like this. And now, if I put at every face, we have like 12 vertices, but 20 faces. This is dual of the dodecahedron, if you want. You can put here like this, 3 vertices. And this 5 one, because you will put everywhere else, will become 10. So you're going to have edges of type 10, 10. The pinky one, they will become 10, 10. But the black edges will be 10, 3. And you have the dodecahedron, which is like 5 connected actually. And then you put a vertex in every triangle, which now we're going to have 3 vertices, vertices of degree 3. Connectivity will drop the 3, so it's 3 connected, but you're going to have edges of 13. So he proved that you have at most 13, and we have examples that is 13, so you cannot improve this, yes. And Lebesgue, this is some guy from analysis, I don't know, he's a Lebesgue, yeah, it's a French guy, famous French guy, yes. He was working on the four-color theorem. And he proved that every connected planar graph has one of these 3 configurations. A vertex of degree 3, so the configurations are like this. Incident with a 5 face, so we have like 5 minus face plus 3 vertex, yes? Or this is the first one. This is the second one. 4 vertex incident with triangle. We have a triangle and 4 vertex. And 5 vertex incident with 4 triangles. So this is a set of 3 configurations which is unavoidable in the class of 3 connected graphs. Unavoidable. That means you give me any 3 connected planar graph, it must contain one of these 3 configurations. That means unavoidable. Here's the definition. Here's the definition, yes. Some set of subgraphs or configuration like this, for a given graph of class of graphs, here is 3 connected, must contain one of these configuration. Any graph from this G class of graphs must contain at least one of these 3 configurations. And in that case, we say it's unavoidable. So what Paul Seymour, Robin Thomas, and all this find how many? 677 configuration. This set is unavoidable. So they reduce the class of graph to internally 6 connected planar graph triangulations, kind of critical graph, others are not. And then they find these 677 configurations, and they are in the same time reducible. We see it like the 2 triangles is reducible. Each of these 677 is reducible, but all together they are unavoidable. So when I have such configuration, I will take it out. I will color it the rest. I will put back which I cut it and extend the coloring. Because it's reducible, I will be able to extend it. Because these all 777 configurations unavoidable, every planar graph, 6 internally 6, blah, 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 must contain one of these. And for any of them, I can do reduction. This is how the full color theorem is proven. So we go slowly. So they take minimal counterexample. They study no 1 vertex, no 2 vertex, no 3 vertex, no 4 vertex. 5 vertex is minimum, okay. No 4 faces, 5 faces, 6 faces, because I can make it triangles. No separating triangle, no separating 4 cycle, separating 4 cycle. So is this something? You have 4 cycle and you have something, vertices inside, some vertices outside. No separating 4 cycle. If we have separating 5 cycle, the inside part must be just a vertex. This is internally 6 connected triangulation. That were the so these people, Seymour and Robertson, they prove a little bit more mathematics first, then Eipel and Haken. This is why they reduce it then from 3,000 configurations and some more, maybe 3,000 to 700. So it's triangulation, yes, minimum degree, what I said is 5, and so on. And they study, I think in the Eipel and Haken also study this 6 and D, C and D reducibility, yes. This is like, we have 2 types of reducibility configuration. The one are very easy, yes. So which one is easier? They're reducible. They're reducible means, let's say the Birkhoff configuration. One such typical configuration is this one, 5, 5, 5, 5. It's a very simple configuration. Okay? And you make first out of, this is one of these 677 configurations. You put first a ring around it, yes? Because this is vertex 5, yeah? You will have like this, 5, you should have another one, this, okay? Because it's triangulation, this is 5. Because this is triangulation, now everything is 5, yeah, because it should be 5. Then you have here cycle. This is the ring. Each of these configuration, you first make a ring. So the configuration actually are bigger. So this is the Birkhoff diamond. But if the real configuration, because this is of degree 5, you extend it to ring and it looks like this. Now you cover this and everything outside at once. It will be colored because it's smaller graph, and then you will get some colors. This some color 1, 2, 3, 1 million possibilities. And if you can always extend these colorings, whatever you get here inside, then it's called dereducible. Dereducible. Low power mode. And sometimes it is not dereducible. Birkhoff is like that. Maybe on the exercise part we could do it. Is not dereducible. So what you have to do in that case? In that case, in order to to decrease the space of all possible colorings that appear around on the ring. You will, as we did before, you will identify some vertices. So I think here you have to identify this, or maybe you identify this one with this one, yes? Something like that you do there, let's say. When you identify and you go back, these two vertices will have same color. And now the space of all possible colorings that appear around will be smaller, and if you are lucky, you can always extend. This kind of reducible configuration is called C-reducible configuration. So sometimes you have to do that trick, yes. And then they prove it for all of these 677, they are C or D reducible, and they prove it with the rules. The rules they apply, here's the examples, okay, Birkhoff, how we do that. This is the legend, what kind of degree vertex is like, that means this vertex of degree 10, that means this vertex of degree 9. The rules that they apply, I don't know how many are here. You can count 1, 2, 3, 4, 5, maybe 30 rules, 36 rules or something. So they use all these 36 rules in the graph, yes, to prove that then this set of configuration is avoidable. But this is not everything. There are like 7, 8, 10 pages like that. There are 70, 77. So for each of them, they prove it's reducible, C-reducible, D-reducible by, you see, by maybe identifying this edge and going back to do reducibility and so on. Each of these configuration has to reduce it separately. Sometimes they use computer to prove it, and so on and so on. So this is how the four-color theorem is proved. Yeah.
Reducible, or
I think they use the computer by to generate all colorings. So you're gonna have a ring on the configuration. Suppose you identify here, and go back to have C-reducibility, let's say. So some of the colors will be vertices will have the same. So let's do like this. So this is your diamond or configuration. This is the ring, and you can take here a random from 1 to 4. Okay, you can say, okay, this vertex is always colored by color 1, yes, and maybe this is always colored by 2. Now you go to generate all these colors, all these possible colorings, yes, and then try to color inside. No, you're proving that this configuration are reducible. Forget about counter example. Now you have something like this. You have something like this, and you have to prove whatever I color have here, I can color this part inside. And here they use computer. This can be bigger. This can be like 20 vertices. So you can always assume here, okay, this is like C-reducible configuration. They identify X2 and X6. You can then assume here you have color 1 and you have color 2 here, yes? Because you get here, yes? And you can fix here, okay, let's make color 1, 1. You can say, okay, let's have color 3 here. And okay, let's have color 2 here. And now you have only 4 possibilities here, yes? But sometimes you can have not 4, you can have 4,000 possibilities. And each of these you can try to check that is colorable the graph. Because maybe each of these colorings, if you have 20 vertices on the ring, if you don't make like by symmetry of colors, you have, like almost 420 colorings. Okay, you can reduce a little bit, not two adjacent color the same, but maybe 3 on 20, let's say. colorings. Now for each of these 3 on 20 colorings, okay, you can fix maybe 1, 2, 3 vertices. It's not 3 on 20, it's or 3 on 70, yes. So you have so many colorings on the ring, you have to check that each of these coloring, you can color inside part. Yeah, and then they use, it's too much, but, sorry?
All of the computation.
Yeah, you don't have to do this. Of course, you need to be optimized, I can always assume that one vertex is colored by 1, and its adjacent is by 2, yes. So I already fixed it 2 vertices, but I have 18 more vertices, which can be like a lot of colors.
First, we need to guess that this should be a reducible configuration.
Sorry?
It's first we need to guess that this should be a reducible configuration.
You should guess. I don't know how to define that, but I think they use computer here to check the reducible. They went, they take the previous guys, this configuration, they make this 5 cyclically, so on. So they were systematically all possibilities, and then for each of them, try is it reducible. If it is not reducible, then you make it bigger. Maybe you make 3, 4 bigger, because this is not reducible. And now you hope, because this is a bigger, you have more vertices, it can be easier to extend. And this is how they did it, systematically, like growing. Oh, if this is not reducible, then I make 5 or 6 new ones, hoping that this are reducible. And if some of them is not reducible, let's say this one, then I make it even bigger on several ways, and then get like 6, 7 more configurations. This is for you to make it under 100 configurations, okay? Finish for today. My time is out. This is for free. I'm only to pay. No, I'm just joking.
Use the diamond. The same trick is applied everywhere.
We can use later, yes. It's the trick, yes?
No, are we using the same trick everywhere? Like the middle as we are removing and adding to the prices.
Yeah, everyone will be great. It's great. So everything is available. We have to add it out. It's not like everyone work just into vertices. You have to sometimes identify more vertices independently. Sometimes you may have to identify 3 vertices. It's a big range. You have to find out yourself. Yeah, it's not easy to think. Yes.
So all the configurations you showed, most of them were derived from the timing. The first one that
you asked the authors. Yeah, it's your way. The business is reusable. Diamond business is reusable. So it's
going to create folder in planar graphs. The dense planar graph, when you are going to have that problems charging.
I have to go to prepare my exercises. Anybody prove Peterson is the smallest mark?
Anybody who has
No, then I have to prove it, okay? In order to do anything else on the exercise, what should we say else? What we should try to prove it?
So, what time will you come?
What time do you want to